So, in the previous class we are here. Rn is a linear convolution between the symbol sequence In and channel model channel model sequence, you can say unit impulse sequence given by Hn. So, I have this discrete time model. This is only model, and that is why it is okay if it is non-causal. Non-causality is not in real time, not for the analog case. How the non-causality comes, I have already explained. So, you have got In, sorry, you have got In and Hn, and you have got Yn, not Yn, I called it Rn. So, let me remove it. Rn is the received sample, okay, sampled at the time capital T plus n tau. That sample is called Rn, that we have seen in the previous diagram, and that is coming out to be this Hr I n minus r. There is a convolution with In. Therefore, if I take in Z transform or Z, which is from here, Z transform is Hz, which is from here, into Iz, which is from here. So, this is the Z transform of Rn, this is the Z transform of Hn, this from Iz. Now, from Rn our purpose is to recover In, exactly if possible, because In is what was transmitted. So, we have to get back from the received samples by doing some mathematics, some algorithm, some operation, we have to get back In. So, in Z transform it looks like this, which means Iz, if you want Iz, you give this Rn, Iz is what? Iz is what you want. In time domain you want In, in Z domain it is Iz, they are equivalent. But Iz is what you want, Iz is equal to Rz by Hz. So, Rz into 1 by Hz. So, if you can create a filter which is inverse of this channel, this thing I call I for inverse, Hij. 1 by Hz is Hij. So, if I can create a filter Hij pass Rz equivalent to Rn through this, I will get In back here, right, where Hij is 1 by Hz. All right. But remember, what is Hz? Hz is actually the Z transform okay. So, in general in this model it is a non-causal system. You have got H0, H1, H2, H minus 1, H minus 2, all that, and also theoretically R goes from minus infinity to infinity. But this Hr actually will not be non-zero or appreciable beyond certain range. If you go to the previous page, you see I called this height, okay, if I take the basic pulse only, if you start from the center point, go tau to the left, I call it H minus 1, 2 tau to the left, I call it H minus 2, and dot dot dot. But you understand, if a pulse is like this, if you go tau to the left, you are here, 2 tau to the left, you are here, 3 tau to the left, but beyond a point, there will be the pulse will become 0, because it is a time bound pulse only, isn't it? It will become 0. So, that is why these coefficients H minus 1, H minus 2, they are progressively decaying, value is becoming lesser and then becoming 0. Similarly, for H1, H2, okay, these coefficients are becoming 0. That is, if you start from the center of the pulse, go tau to the right, whatever is the contribution, okay, for the basic pulse, you call it H1, then next to tau to the right, you call it H2, but pulse is a decaying pulse. As I told you, it is a time bound decaying pulse. So, beyond the point of time, it vanishes. As a result, H1, H2, they also goes out. So, therefore, theoretically the summation is from r minus infinity to infinity, but in practice HR is 0 for r may be greater than some L and or less than minus L. Okay, there is a range from minus L to plus L, that is where it is confined. This is not equal to 0, otherwise it is 0. Oh, sorry, this is okay. This is equal to 0 outside this range, which means HR could be something like this, some value here, some here, some here, some here, dot dot dot, up to L its value is decreasing, and here also. My drawing is not correct, maybe I redraw it. It will be a decaying function, right? So, I should show that in my diagram. This is L, very small value. Similarly, on this side may be and then zeros. So, this is my range L 2 minus L. Okay. Outside, in practice, it will be 0 after that. So, then that means HR actually is an FIR filter, finite impulse response filter. HZ has only zeros, right. So, 1 by HZ, if I now substitute HZ here or from minus L to capital L, this thing here, okay. Zeros will become poles, zeros of this is an FIR system, it has zeros only, okay. But now it is HZ comes in the denominator, so zeros will become poles, and therefore HIZ is an IIR system. HIZ is an IIR system, because IIR systems have poles, okay. But again, what will happen? I do not know what the poles are, because after all capital HZ is coming from this HR. HR is what? HR we have seen, they are coming from these pulse heights at various sampling points, but this is a distorted pulse. I have no knowledge about the distorted pulse, I know about the transmit pulse, that is what I had designed. But the channel is largely unknown to me, its property, that is impulse response also changes from time to time. So, what is P prime T I do not know, therefore, what are these coefficients I do not know, remember. Okay. That is why in the end we will require adaptive filters, because these coefficients are not only not known, they change with time. All these H0, H minus 1, H minus 2, all that, H1, H2, all that, right. Now, so this is a typical HR, it is a FIR system, finite impulse response. It will have zeros. If I have 1 by HZ, it will be in general poles, having poles, because zeros become poles. So, HIZ which has poles will definitely be IIR. Okay. IIR means in the complex Z plane, if it is a unit circle, some poles may be here, some poles may be outside. So, you can look for that solution which has which has region of convergence here. At least that will guarantee one thing, that region of convergence includes the unit circle, and therefore, it is stable system. But this will be non-causal. Okay, this will be non-causal because it is not, it is within two circles, outside one inner circle, inside another outer circle. So, there is a non-causal but stable system, but stability at least guaranteed. Non-causality is an issue. Okay. So, suppose we try to construct this Hij, and assuming suppose for a moment that Hz is known to us. So, Hij, which has various possibilities, we try to construct this stable but non-causal one. Okay. Now, if it is stable, then what happens? If Hij has impulse response Hin, okay, which is causal, which is stable but non-causal. But one thing is there, non-stable means if you take its absolute value of the samples and equate and sum, this is finite. This is the condition of stability, absolutely summable. This is all from basic DSP. And system, a linear time invariant system is causal. If you take its impulse response, take the mod on that and sample and sum over all. If that is finite, then it is stable. So, I am looking for this solution, because you can have Hij, you can calculate its inverse jet transform for various ROC, region of convergence. One ROC is between these two circles. Here the pole nearest to this unit circle, here the pole nearest to the unit circle, in between there is no pole, take that to be a region, one region of convergence that includes the unit circle. So, if you take the inverse jet transform over this region of convergence, you will get Hin, which will be non-causal, I agree, that is why n from minus infinity to infinity, but it is stable. Stable means there is one thing, that Hin cannot remain high for all n. As n increases, it has to die down, finally it becomes 0, then only summation will be finite. If it still remains appreciable, even if n goes up or up to infinity and minus infinity, then the summation will not converge, summation will not be finite. Okay, summation will not be finite, which means for stable system, since it is since we need this, it implies Hin tends to 0 as n tends to plus or minus infinity. That is, as we go towards plus infinity or minus infinity, this Hin values have to go down, and then only the summation you can work out, it will converge. But if Hin does not go down, suppose it remains constant at 1 on either side, plus infinity and minus, summation will not converge. So, therefore, if you are looking for a non-causal but stable system, one thing is there, that Hin, it will be having values like this, but it will go down, maybe up to some n minus 1 and minus n minus 1, like this, and after that 0, 0. All right. Still, this is not realizable in time, because this is non-causal. This is non-causal, right? But one thing is there, suppose I use this, and on Rn, Rn is to be passed through a filter whose impulse response is Hin. See this, Hn, that is the inverse filter. Always 1 by Hz, I call it capital Hij, corresponding impulse response was Hin, I for inverse. So, Hij, which is 1 by Hz, corresponding impulse response is Hin. So, if I have to pass Rn through Hin to get back In. So, that is here Hin, but this Hin I have done some approximation, I have truncated it I am assuming values to be 0 to the right of capital N minus 1 s point and to the left of minus capital N minus 1 s point. Okay. And through this Rn if I pass and if my approximation is not bad, I should still expect to get IN. So, I have to construct this filter. But here problem is if I have to run it in real time, because I will be doing real time processing, I will be requiring future symbols, okay, because of this non causality. To get rid of this thing, what I can do, suppose instead of HIN, I construct a filter. Suppose I construct a filter not HIN, but z to the power minus n minus 1 HIN. All right. Then what will happen? This is a sequence in Z domain. Let me write it in Z domain only. That means this entire sequence will be shifted to the right by capital N minus 1 point, because I am multiplying Hij okay, in Z domain by Z to the power minus N minus 1. So, in time domain it is just a shift operation by N minus 1. What we will do, this will become, this will come at 0, the entire thing will be shifted, you know. It will go up to some point. So, just twice N minus 1, up to this it will go, but this is a causal system. So, if instead of this filter I construct this filter, then there is no problem with my practical realization, because it will be causal. But Rn, what it will give? Now, this is a system which is equivalent to having Rn here. You can say first I put Hij and then z to the power, this z to the power minus n minus 1. But I know from here, from this diagram, if Rn is passed through Hij, I get my In, and now In delayed by capital N minus 1. So, it will be In minus. So, this filter will give me an output which is transmitted sequence, but a delayed version. And if I know this capital N or N minus 1, I know amount of delay. So, from the received, from this waveform at the output, I can make the correct decision. Okay, I know what it is, because if I know how much this capital N minus 1 is, then I know what is the delay on ideal In. So, that way I can get back my In. Okay. So, this is the filter that we have to design. Unfortunately, we cannot design the filter because it requires knowledge of Hij. Hij is an inverse system. From here is an inverse system, right, 1 by Hz. If I have to know Hij, I must know Hz, but Hz is for the channel, and channel impulse response is not known, and they change from time to time. As a result, Hij is not known, and therefore, this filter is not known, this overall filter is not known. Therefore, we have to use our adaptive filter technique. This is not only not known, this changes from time to time. So, therefore, we have to use an adaptive filter technique to obtain this, all right. So, that will lead to what is called adaptive equalizers. In an adaptive equalizer, there is one mode called training mode, adaptation mode. During that time, transmitter transmits universally standard training sequence called pilot sequence. Transmitter Tx, it transmits some sequence, okay, some training sequence, all right. maybe you can call it SN, some pilot sequence. Standard known to receiver. So, receiver knows what is transmitted. It will go through channel, channel means the channel model. Channel model, because I am considering the discrete time thing. Let me use this notation. I am using the index and the subscript, not within bracket. So, Sn. So, what you receive is Rn, but you know what Sn is. So, you construct a filter and this Sn which is known to you, you delay it by this amount. So, this is a filter you design, optimal filter, okay. You design so that output is a good estimate of this. So, in this case we know the model. If Rn is passed through this and then delay, then you get back this thing, right. So, therefore, I am giving the same Rn and this is what was transmitted. So, I want the filter to produce that or something very close to that, a good estimate of that. So, this I give to be the, this is known to me because during training mode, this is called training mode, I know, I the receiver know what was transmitted. There was some S sequence. So, S n minus within bracket capital N minus 1, that I give as the desired response. For that I derive the optimal filter, okay, with Rn input. So, that should give me this, because then only optimal filter output and this transmitted sequence, this thing they are same and therefore, error will be 0. That is why. Okay. So, this and this will be close to each other and there will be 0. Okay. So, this is the optimal filter. The problem is optimal filter requires knowledge of the statistics of these and all that, but this again requires channel information, because statistics of this depends not only on the statistics of this autocorrelation, it will also depend on the channel, because Sn goes through channel then only becomes Rn, and those are not known to me or they vary from time to time. So, I make it adaptive. So, there is a training mode, this is called training mode. What happens is from time to time, maybe after every half an hour, training mode takes place. During that time, transmitter transmits one known sequence of symbols called pilot sequence, which is standard and known to receiver. So, receiver knows now training is going on. So, as Sn goes through this channel, you receive Rn, Sn is known to you. So, you want to make an optimal filter of the right order, so that output is a good estimate of this. Like I mean, if it is a correct inverse system, then the output will be just delayed version of what was transmitted. So, this delayed version, delay by capital N minus 1, delayed version of Sn which was transmitted is taken as the desired response, and then I try to find out the optimal filter, and that I do using the adaptive filter route, because I cannot directly compute the adaptive filter because optimal filter, because it will require autocorrelation matrix knowledge of the input, that I do not know, because input comes through channel, I mean comes not only from Sn, it uses information about, it has information about the channel which is not known to us. So, you have to make it adaptive. So, what do you do during the training mode? Okay, during the training mode, we use this adaptive filter, and we have got W0, W1 up to some appropriate P, and all these coefficients I adapt. So, I run this adaptation for that, for the overall training mode. So, some time is given to me, some nanoseconds. During that time training is given, because and then again whatever values I get, I remain happy with them. For the next half an hour maybe I use them. I assume that channel is not changing during that half an hour. So, they will do pretty well. So, for now you transmit your real sequences, music or speech or whatever, you receive distorted sequence RN, but using this inverse filter you get back here a very good estimate of what was transmitted. Delayed of course, but delay does not make any difference to me. Okay, this delay is hardly appreciable in real life. So, this is what happens during training. Okay, this is what happens during training, and this training mode is called supervised mode. Okay, supervised because this is a supervising signal. The desired response is already known to receiver, it is stored in receiver because this is a kind of a constant universal knowledge. It knows what was transmitted. Okay, from its own storage it uses this, and this is a kind of supervisor which helps in carrying out the supervision, adaptation. Now, after the training mode, still we can do something. So, we use a switch. During training mode, this desired response come as it is n minus 1. But once the training mode is over, this comes from 1 minute. Let me explain what this is. Suppose training mode is over, now you are transmitting your real stuff, speech, music, whatever, they get distorted and then using this inverse filters, which I believe they model my HIN correctly, I get back values which are close to what was transmitted. So, I may get not SN, I may get SN cap here, but SN cap will then be passed through a quantizer. Quantizer means I know what was transmitted were discrete levels, either this value of voltage or that value or that value or that value, nothing in between. Okay. So, on this scale maybe I have got either this or this or this or this, like that. So, around each I have a band, around this I have a band. So, suppose SN cap is somewhere here, this is actual SN and SN cap is here. So, this quantizer will correctly quantize it to this value, because this is zone. Okay. So, this quantizer output I take as trainer with of course this much delay. So, during training mode I take it from this, I take this to be my supervisor training sequence. Once training mode is over, still I carry out some kind of adaptation by using this and a delay. This delay is required. From here. So, assuming it was correct, okay, and this is not S cap n, sorry. Okay, I am making a mistake here, so let me correct. This does not produce S cap n, it produces S cap n minus, it produces an estimate of this, which means I won't require this delay. Because this optimal filter which is basically adaptive filter here, it will produce a good estimate of this desired response during the training. So, it was not n, it is n minus a delayed version capital N minus 1. So, it will be an estimate. So, just S cap of n minus capital N minus 1 that, and that will go through this, and hopefully it will be quantized to the right value. So, that will come here as desired response. Okay, that will come here as desired response, because what we are targeting then is this. First, let me make it adaptive. Adaptation, the error has to from here. During training mode, this switch moves here. So, what happens is already what was discussed here. This is my stored sequence, delayed version. This is taken as a supervisor, that is training sequence. That minus the filter output. Filter output is a good estimate of this, because that minus the filter output is the error. That error variance is minimized by this adaptation loop, and I get a good estimate of this. That is fine. That happens during your training mode. Once the training mode is over and you are transmitting your speech and music and all those signals, still I carry out some kind of adaptation. What happens? Whatever comes out here, okay, that will be passed through quantizer, and even if this has some error, because this may not be exactly equal to this S n minus within bracket n minus 1, okay, that is a transmitted thing with a delay of n minus 1, because of all the approximations and all, and maybe some noise effects, it will be, I mean, there will be some difference, but the difference is not much, it still remains in the correct band. Then after quantization, it will come back to the correct level. So, correct level will come here. So, correct level minus its estimated thing. That error also we want to minimize. That is why this adaptation loop. So, if I minimize the error, that means S n cap and its true value, there is a quantized value, they will remain in the same band, it will not fly off to other bands. So, I will make correct decisions. What does this loop do? It tries to minimize the error variance here. That means S n cap and its true value, they will be, which is coming through this path, they will be close to each other, which means this will not fly off to other band, and therefore, I will not make error. After quantization, I will quantize it to the correct value. That is what is achieved here, and this is called decision, this adaptive filter, this is called decision directed mode. Again, after half an hour, you switch to training mode, carry out this kind of training. Then once that is over, then again switch this way. So, estimated value of transmitted symbol with a delay, that quantized, and if it is quantized to the correct value, that minus this error, I want to always keep minimum, so that they are very close to each other and this fellow does not fly off to other band, and that is done by this optimal filter, which is adaptive filter here. Okay. So, that is a very good example of this thing, modeling inverse system, because after all equalizer is that inverse model HIN, not HN. Okay. So, I covered several important applications. Now, again in the next class, I will come back to analysis, some analysis of that elements algorithm convergence. We proved convergence in mean, but you have to see that around mean, if it fluctuates, how to control the range of fluctuation, so that it remains close to the optimal value. That is what we will target in the next class. Thank you very much.